Welcome to Who's in STEM. And I'm Ken Ono, your host and the STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics at UVA. Our goal is simple, to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics.
And the world is made of energy, and the world is electricity, and the
You're listening to the song Energy, written and performed by my former PhD student and Michigan Tech professor Robert Schneider and his band Apples in Stereo. The song, as you could guess, is about the ubiquity of energy. Everything in the universe is made of energy, including us, people.
is made of energy, and there's a lot inside of you, and there's a lot inside of me. It's gonna be.
And this isn't hyperbole. You see, energy and matter, they're the same entity. Isn't that the content of Einstein's famous equation, E equals mc squared? Well, today we're talking about all energy, and hence, all matter. We're talking about cosmology, the astronomy and physics that aims to reveal the origins of the universe. According to astrophysicists, our universe was created at a singular moment in time, something like 13 or 14 billion years ago. All energy was crammed into a single speck, which exploded with unimaginable force, creating matter, creating the galaxies, creating the planets and stars, and ultimately creating us. And I'm talking about the Big Bang. Wouldn't it be magnificent if we could reach back in time to witness the beginning of the universe? To be there right after the Big Bang? What would we see? What would we learn? Well, UVA's Bradley Johnson, Associate Professor of Astronomy, is doing just that. Now, he doesn't have a time machine, but he's a world expert on cosmic microwave background, known as CMB, and it's the faint glow of the flash of light that burst from the early universe. Brad, welcome to Who's in STEM.
Hi there, thanks for having me. I'm really excited to be here and to chat about all this stuff.
So, Brad, as a scientist, we need evidence. In fact, the nature of evidence is so important to us in everything that we do. So, what evidence can you show us that supports the Big Bang Theory?
Sure, so maybe we'll start off with what is the Big Bang? The Big Bang is a name that was coined by Fred Hoyle in 1949, describing the beginning of the universe. So prior to the 20th century, it was commonly thought that the universe was static and infinite. You look out at the night sky, and that's basically what you see, so that's why everybody thought that. But Newton had proposed a theory of gravity, which had some problems, and so Einstein and others were working on developing a newer theory of gravity, which ultimately came out as general relativity in 1915. And so the idea here is that gravity is described as curved space-time, which is pretty mind-bending and complicated. But this theory predicted lots of different things, including gravitational waves, gravitational lensing of light, and space-time expansion, which means the universe could be expanding. At the time, nobody liked this idea, right? It was
Scary.
Everybody thought the universe was static, and now there's this new theory from Einstein that says the universe can be expanding. But what we found in the early 20th century, Edwin Hubble in 1929 observed what he called extragalactic nebula. We didn't know there were other galaxies at the time, so that's what he called it. He was just observing these blobs, and he noticed that they were moving away from us in all directions. What that led to was the discovery that the universe is expanding. So Einstein's theory that predicted the possibility of the universe expanding was actually discovered a short time after that, right? And so if the universe is expanding and everything's moving away from everything else now, in the past, if you reverse time, then everything comes together, right? And at some point when everything comes together, it gets hot and dense, molecules break down, atoms break down, and you wind up with what we call a plasma. So if the early universe is a plasma, then the prediction is that you should be able to see this plasma everywhere. And when you look at the sky, you don't see anything. It's black at night. In the mid-20th century, 1965, Penzias and Wilson published a result where they found this exact plasma. It was in the microwaves, though. It's not in the visible wavelength. And so the way they found this was there was a 20-foot reflector antenna that was built by Bell Labs. It was originally for long-range communications. And then when it was done, they decommissioned it and gave it to radio astronomers, Penzias and Wilson. And they were going to map the galaxy, right, and learn about what the galaxy looks like in microwaves. And they pointed this instrument in various directions, and they always found this background. There was a signal there that they weren't expecting. So the famous story is they thought for a while it was pigeon droppings in the telescope. And so they went in and cleaned the telescope, and they couldn't figure it out. And so everywhere in the sky there was this background. So they eventually went to their colleagues at Princeton and said, we've discovered this signal. Do you know what it is? And they said, we know exactly what this is. We've been working on this. This is a prediction from the Big Bang. You should see this. And so this was a great discovery. This led to a Nobel Prize for Penzias and Wilson in 1978. And then more recently, Jim Peebles at Princeton, won the Nobel Prize in 2019 for his contribution to all of this.
It's really quite remarkable how Einstein's revolutionary and brave thought has really transformed how we do science, and it continues to do so today. So you're part of that story. So,
Yes.
Brad, you've been in the news. It's been widely reported that you're a key player in a huge $53 million NSF grant, adding to the incredible support from the Simons Foundation based on an observatory in Chile. Congratulations. Tell us about it.
Yeah, thanks for the congratulations. This is really exciting. So the Simons Observatory is a new observatory that we're building. It's funded by the Simons Foundation, which is how it got its name, and the Heising-Simons Foundation, but also university partners like UVA, and now the National Science Foundation has joined the effort. So when it's completed, this observatory will have one 6-meter telescope and 6 half-meter telescopes that are all working together to observe the CMB.
CMB, again, that's cosmic microwave.
Cosmic microwave background, that's correct. So the observatory is being constructed at an elevation of 17,000 feet on Cerro Toco in the Atacama Desert in Chile. So you might ask, why there? The problem with microwaves is they interact with water. So this is how your microwave oven works. You put your food in the microwave, you turn it on. The microwave oven is actually generating light. The light interacts with the molecules in your food, and it excites them, it heats up the food, and that's how it works. So it's the same kind of a story here, except the microwaves are coming from space, and we want them to get into the telescope, but they have to travel through all of the water in the atmosphere, and the water in the atmosphere gobbles up that light signal. So the best thing to do is to go into space, but that's expensive, and so that space-based telescopes tend to be sort of capstone projects. If you're doing pioneering work, you do it from a ground-based site. And so we're using the site in Chile because it's high. We're getting above the atmosphere. And so we're getting away from the water because it's a desert, and so it's very dry. So we're building this observatory right now. Next year, we're hoping to make our first observations. This is a collaboration with over 300 scientists from around the world and 45 institutions, including UVA. And so my research group at UVA is focused on building telescope parts. So I tend to focus on instrumentation.
So you're an instrumentationalist.
That's right.
But also a cosmologist, physicist. You do it all.
That's
Well, in
right.
your field, you have to do it all.
That's right. That's
Yeah.
very true.
So let's talk about telescopes. So as a kid, I had one of those little white cardboard telescopes, right, with a little 4-inch mirror. Probably cost $20 back then. I got it at Toys R Us. But people have heard of Arecibo in Puerto Rico, Hubble, of course, the recent James Webb telescope, and the Chandra X-ray telescope. Tell us about these. Why do we need so many different kinds of telescopes, and how is your telescope different from all of these?
Right, good question. So the electromagnetic spectrum describes light. And so you can have different wavelengths of light. Long wavelengths of light are radio, and short wavelengths of light are X-rays or gamma rays. And visible wavelengths are right in the middle. And we can actually only see a small slice of the electromagnetic spectrum with our eyes. But we know these other wavelengths are there. Wi-Fi, for example, is radio. Everybody's using Wi-Fi every day to communicate. There's Wi-Fi photons, particles of light are called photons. There's Wi-Fi photons bouncing around your home all the time, right? X-rays, similarly, if you break your arm and you go to the doctor, they use X-rays because the X-rays can go through your arm and give you an image of the broken bone. Visible wavelengths are in the middle, and we need a range of telescopes for all of these wavelengths so we can study different things, right? There are different physical processes that appear at different wavelengths. And so we need a suite of telescopes to disentangle the full story.
Awesome.
And so for Arecibo, for example, that's radio. For Hubble, that's visible wavelength, near infrared. So that's been great for doing galaxy work. The Webb Space Telescope is infrared. Right, I'll come back to that in just one second. Chandra is an X-ray telescope. So again, you can see each of these telescopes is visiting a different part of the electromagnetic spectrum. There's an interesting phenomenon, though, and this goes back to the microwave background story, and that is with the expanding universe, right? Things that are far away from us are moving faster and faster. And so the Doppler effect, which you're familiar with, when you hear a police car coming toward you, the pitch sounds high. When the police car goes past you, the pitch sounds low. So this is the Doppler effect. So when you have motion and you have waves, you get wavelength shifts, right? And so when you have light coming from outer space, right, you get the same effect. The light gets red shifted, we call it. Right. And so things that are far away get red shifted. The reason we can't see the microwave background, the reason why it should be a visible plasma like the sun, but we can't see it is because it's moving away from us. So that's why the sky looks black. But with all these other telescopes, right, one way to think of it is longer wavelengths allow you to look further out into space. So the Hubble Space Telescope is visible wavelength. We could see so far out into space. If you want to look further, you have to take into account this Doppler effect. And so you need a new instrument to be able to help you look further. And that's what the Webb Space Telescope is doing. It's allowing us to probe deeper into space. And then what I'm doing is it's tuned for a wavelength that's the farthest thing you could possibly see. We're looking at essentially at the horizon of our piece of the universe. So we're looking back in time, and we're looking out as far as we possibly can. And we'll see what the universe looked like 13.8 billion years ago. This is the surface that we're observing is actually a transition point. So when you look out into space, the further out you look, you're actually looking back in time. Okay? So for example, we're here talking, and we don't see each other instantaneously. We see each other in the past, right? Because light takes a certain amount of time to travel from one point to another. So when I'm looking at you, I see you not right now. I see you about a nanosecond ago, right? And we perceive that as instantaneous. The sun is a bit more dramatic. When you look at the sun, it's about 8 light minutes away, which means light from the sun takes 8 minutes to get here. So if the sun exploded right now, we wouldn't know about it for 8 minutes, which is a little frightening, but that's true. You can play this game as you go further and further out into space, and as you get to very, very far distances, right? When the light gets here, it's carrying an image of that thing in the past. And so we're able to look back in the past, exploiting this phenomenon.
That's a frightening thought. So there are things that are written in time that haven't yet reached us. That's
definitely.
Really, which is the
definitely
point of your work.
That's
right?
exactly right.
So tell us in a little bit of detail about the stuff that you're building. Yeah.
So we're building the telescope parts. In particular, I really like the detector system. The detector system is kind of fun because it's very challenging. So we're looking at a thermal signal that the temperature is 3 Kelvin, and we're looking for fluctuations, small fluctuations in a 3 Kelvin signal. So a quick way to think of it is that means your detector system has to be cooled below that temperature. So what is 3 Kelvin? 3 Kelvin is minus 450 degrees Fahrenheit. It's incredibly cold. And so we have to cool our system, our detector system, down to that temperature to have any hope to detect the microwave background. So this is what we're making. We're making telescopes that are cooled to these incredibly cold temperatures, and we're deploying them to 17,000 feet in Chile. It's an experimental challenge. But what I like about it in particular is the device physics. We use superconductors, we use microwave electronics. There's all kinds of interesting technology pieces that didn't exist until now. We're inventing this stuff. You don't go to the store and buy millimeter wave detectors, right?
It's not Radio Shack with your soldering iron.
Exactly,
right?
Exactly. This is all custom stuff. So we have to design this stuff, build it, and deploy it. It has to work, right? And this is actually one of the things that I love about the field. Is that, a lot of times you talk to people and they get a degree and they say, oh, I got a job and I never use the knowledge I gained during my degree. I use every single piece of knowledge that I gained when I was in college and in graduate school, because we have thermal physics, we've got microwave electronics, we've got cosmology, there's general relativity, there's special relativity, statistical mechanics. Everything is rolled up into one one endeavor. And that's incredibly satisfying to be able to think about so many different things every day.
Yeah, I'd love to visit your lab. What kind of tools? Right, this is not like Tool Time, the TV show. Well, so Brad, did you always know that you wanted to be a cosmologist? Tell us your story.
Yeah, that's a good question. So I've always been interested in cosmology. I've always thought about the universe. And I remember when I was a kid thinking about it was sort of mind-bending. It was very confusing, and so I think I spent a lot of time thinking about it. But I started out at Bethel College. I got a degree in physics, and I was pretty sure I was going to go into industry. That was my plan. I was going to just make widgets at some company. But I had this sort of passion for cosmology, at least in the back of my head. But I didn't know you could really do this for a job. And so when I got to my junior year, I read a book called Black Holes and Time Warps by Kip Thorne, who just recently won the Nobel Prize for discovering gravitational waves with Ray Weiss and Barry Barish. It was fascinating. I got halfway through the book, and I put it down. I said, I don't need to read the rest of the book. This is what I'm going to do with my life. And so I very abruptly changed course and started applying to grad schools, where I eventually went to the University of Minnesota. And the story there was interesting. I knew I wanted to do cosmology. This was now my new passion. But I didn't really realize how grad school worked.
You got used to cold temperatures there, maybe not 3 Kelvin.
That's right. That's exactly right. So I didn't really know how graduate school worked, and so I wasn't paired with an advisor. And so my first couple of years, I was kind of searching for the right project, given my passion. And so I wound up doing an observing project during one summer in Australia at the 73-inch telescope at Mount Stromlo. We were doing gravitational microlensing studies, which goes back to the GR prediction. Mm-hmm. So that was interesting. And at the time, I would be sitting in the chair in the control room all night and observing. And night in the control room was day in a work day at the University of Minnesota. And so I would have my email window open, and I would see all the email traffic for the day. And as I was sitting there, I got an email that said, we just hired Shaul Hanani, who does CMB observations. So he was doing instrumental stuff and cosmology. And I read the email, and I said, this is the guy. This is happening for me. This is perfect. So I sent him an email 5 seconds later, and I said, could I be your student? And he said, sure. Wow. So sight unseen, we became partners, and we've been working on things together for the last 20-plus years.
Oh, great story. Great story. Well, we have to start wrapping up here. It's been a wonderful conversation. So I have to ask, for interested UVA students here on grounds, how can they get involved?
That's a good question. I have a lot of projects that are suitable for undergrads. So all of this sounds complicated, but there's a lot of technical things to do. There's a lot of technical projects. And in fact, I have a lot of undergrads right now this summer working with me. So if you're interested, you can certainly send me an email and let me know you're interested, and we can try to find a way to get connected.
Great. Maybe they'll get a trip to Chile.
Yeah, right. Yes, that's right.
Well, Brad, this has been great. Thank you. You are a stellar, pun intended, you're a stellar example of President Ryan's vision for UVA to be great and good in all that we do. And thank you for your dedication to UVA, and Godspeed in your research. I'm Ken Ono, STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics, and you've been listening to Who's in STEM.
Who's in STEM is a production of WTJU 91.1 FM and the Office of the Provost at the University of Virginia. Who's in STEM is produced by Catherine Kosoboom, Ria Verma, Mary Garner McGee, and Catherine Hansen. Our music is composed and performed by Robert Schneider and John Ferguson of Apples in Stereo. Listen and subscribe to Who's in STEM on Apple Podcasts, Spotify, or wherever you get your podcasts. We'll be back soon with another conversation about scientific and technological innovation at the university.